We present Lepard, learning partial point cloud matching in rigid and deformable scenes. The goal is to establish point-to-point correspondence between real-world range sensor measurement, such as the Kinect camera or the LiDAR scanner. Point cloud matching is an important component in many computer vision tasks. In rigid scenes, point matching can be used to estimate camera position for SLAM systems. In deformable cases, it facilitates dynamic tracking and reconstruction. The standard point cloud matching pipeline consists of two phases. Point cloud feature extraction, followed by nearest neighbor search in the feature space. State-of-the-art point clouds matching approaches employed the geometry features extracted by 3D convolutional neural networks, such as the KP-conv-based or the Minkowski engine. These feature extractors are strictly translation invariant, and, to a certain extent, also invariant to rotation transformations given the commonly adopted max pooling layers in the networks, and random rotation-based data augmentation during training. Transformation invariance is good for local feature representation. However, it may cause ambiguity in scenes that have repetitive geometric patterns. For instance, in this example, the flying dragon has a bilateral symmetric shape. The color shows the visualized feature. The feature is produced by Predator, which is based on the KP-conv. Predator learns similar features for the two wings of the dragon. Such features lead to ambiguous matching results. We argue that such ambiguity could be resolved by enhancing geometry features with the 3D positional knowledge. To leverage 3D position information, we design our method with the following features. First, the position is transformation variant. It should be disentangled with the transformation invariant feature. Second, to find correspondence in close regions, we use the position encoding that can reflect the relative distance between 2 points. Finally, we introduce repositioning to adjust the cross-point cloud relative positions. Given the input point cloud S and T, we feed them through a KPFCN backbone which subsample the point clouds and extract the geometry features. The point clouds are encoded by a positional encoding function, theta. We use the rotary positional encoding proposed by Su et al. And extend it to the 3D case. Theta encode position in an absolute format, but the inner product between two encodings explicitly reveals the relative 3D distance information. The position codes and geometry features are then processed by a TMP layer which includes a transformer, matching and progress layer. Inside the TMP block, the position and features are passed through the transformer block with a self-attention followed by a cross-attention. To ensure position and feature are disentangled, we hold them in separated data streams, such that position can guide the attention matrix computation but cannot be a part of the feature. Then we compute the confidence matrix between position encoded features. Given the confidence matrix, we select the top n matches and fit them with rotation and translation using soft progress. With the estimated rotation and translation from the soft progress layer, we update the positional encoding of the source point cloud. We call it repositioning. As shown in this example, repositioning pushes corresponding points closer in the position space, such that it better informs cross-attention. Given the updated positions and transformed features, we use the second TMP layer to predict the final matches. We apply Lepard for both rigid and deformable point cloud matching. For rigid benchmarks, we use the 3D match and 3D low match, which captures indoor scans with different ratios of overlap. However, for deformable cases, such a benchmark does not exist. To this end, we propose 4D match. We generate partial point cloud scans by synthesizing depth images from deforming things 4D. We split the data as 4D match or 4D low match based on an overlap threshold of 45%. Here we show a scan registration result on 3D low match. The feature visualization shows that our approach learns a position-aware feature and also accurately reflects the interpoint cloud relative position. Our method alleviates the matching ambiguities for this bilateral symmetric dragon. Note that our method produces different features for the left and the right wings of the dragon. Our method achieves state-of-the-art non-rigid point cloud feature matching results on 4D match, and shows superior better results than other related approaches, including probabilistic registration, functional map-based, and scene flow methods. Here we show demos of registration in both rigid and deformable cases, using the predicted matches. Low overlapping cases are still challenging for both matching and registration. Our method fails if the point cloud undergoes non-rigid transformation and has limited overlap. Thanks for watching. Please check our paper and code for details.